सहनावतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We begin this lecture continuing our discussion on the assignment problem. We have already formulated and solved the assignment problem using the Hungarian algorithm. We have also seen how the Hungarian algorithm works and how it provides the optimal solution to the problem. We have also shown that Hungarian algorithm is an example of a dual algorithm like dual simplex. It finds a feasible solution to the dual of the problem, and once the primal becomes feasible, the optimal solution is obtained. There is still a couple of things to be seen with respect to the assignment problem. The first thing is, unless otherwise stated, the assignment problem is a minimization problem. Remember that the assignment problem has a minimization objective of minimizing double sigma Cij Xij. There could be situations where we have to solve a maximization assignment problem, and what we do there is we convert it into a minimization problem by simply multiplying the objective function coefficient with -1. For example, if we had a maximization assignment problem, say with numbers such like this, we convert it to a minimization problem by multiplying the objective function coefficients with -1 and then we can do row column subtraction from this matrix and proceed as it is. Normally it is not recommended to do the row column directly for maximization problem. It is always better to convert it to a minimization problem, treat this as row minimum and subtract from every element and so on. The assignment problem usually is a square matrix. We have seen this is a 4 by 4 example where 4 jobs have to be assigned to 4 people. Unless otherwise stated, the assignment matrix is a square matrix, but we could have situations where we could have, say for example, 5 jobs and they might have to be allocated only to 4 people. For example, we could have a 5th job which might have something like 7, 6, 5 and 8. Now in situations such as this, we need to convert this into a square matrix by adding a dummy as we did in the transportation. The dummies will have 0 and then we proceed. After converting this into a square matrix, we proceed as we normally do. This problem being a maximization problem, we go back and we need to write this. We do not put a dummy here. This will become -7, 6, 5 and 8, and then we could also put a dummy here and convert it into a 5 by 5 problem. Sometimes we could have an assignment problem which has 4 rows and 5 columns, in which case we add an additional row which will be a dummy row, make it into a 5 by 5 problem and then solve. The only thing that will happen is if we have an unbalanced assignment where the number of rows and number of columns are different, then either all jobs cannot be assigned to all people or all people will not get a job. For example, if I have 5 jobs and 4 people and then we make it into a 5 by 5, now whichever job is allocated to the dummy is effectively not allocated at all. Similarly, if there are 5 people and 4 jobs, then in the final solution one person does not get any assignment. But when we solve an assignment problem, we have to convert it into a square matrix and then solve. There could be situations where a particular job may not be performed by a particular resource. For example, if this is a minimization problem, and say it is a 4 by 4 minimization problem, and suppose we say that this job cannot be performed by this person, then we put a big M here. Big M as we defined M in the simplex. Once again M is large and positive and tending to infinity for a minimization problem, so that when we make the allocations we will not have an allocation at all here. This M plus constant is equal to M, this M minus any constant will be equal to M. So this will never get 0, therefore this can never be a place for allocation. So this way we handle situations where a particular job cannot be handled by a particular person. The last thing perhaps that we need to look at is this. Now when we formulated the assignment problem, this is the objective function. We have constraints sigma xij equal to 1, sigma xij equal to 1. We defined it as xij equal to 0, 1. So summed over I for every j and summed over j for every I. This is the formulation of the assignment problem that minimizes the total cost of assignment. Now these two constraints indicate that every job goes to exactly one person and one person gets exactly one job. It is a square matrix with n square decision variables. Now the only thing that one more is this 0, 1 is now relaxed and this problem is written as greater than or equal to 0, it becomes a linear programming problem. And if we solve this linear programming problem by simplex or any other linear programming solver, then we would still get solutions where these xij's actually take either 1 or 0. We will not have a situation where these xij's will take fractional values. Now xij will continue to take 0 or 1 even if we relax the 0, 1 restriction and solve the resultant LP. Now this is very similar to what we saw in the transportation problem. We also saw in the transportation that we had AIs and BJs, and we said that as long as the AIs and BJs are integers, we said the solution to the transportation problem would be an integer. Now here we have 1 here which is an integer, so solution to the assignment problem even if we solve it as a LP would still be integer valued, which is a 0 or a 1. However, we do not solve this using linear programming because we have a very degenerate LP. There are n square decision variables out of which only n variables are basic at the optimum. So we use different methods such as the Hungarian algorithm and solve the assignment problem. So with this we come to the end of our treatment on the assignment problem, and we look at the next topic which is called dynamic programming. Now under dynamic programming we are going to try and solve different examples to show to you the various terminology that are associated with DP. Now in dynamic programming we divide the problem into several stages and solve the problem for each stage. Now we go back and see the dynamic programming is used when the given problem can be solved in stages. Here the decisions that are made in a particular stage will affect the decisions at the subsequent stages, but they are dependent on one another. We also follow something called a backward recursive approach in dynamic programming. What we are going to do is we will illustrate the concepts of DP, idea of the recursive approach, and the terminology that we are going to use, including the notation, by using an example which is called as Stagecoach problem. So we will solve the Stagecoach problem first, and then we explain the terminology as well as a general framework to solve all DP problems. Now Stagecoach problem is essentially the problem of finding the shortest distance from a given source to a given destination, which is nothing but the shortest path problem. So we take a Stagecoach problem which is like this. Now we have 10 nodes or 10 cities that a person has. Person is right now at the start node or city 1 and wishes to go to the destination node or city 10. Now this is the network that is connecting the nodes. This is a problem where you can easily decompose the decision making into different stages, and you will also realize that here you do not actually have a connectivity between say 1 and 5 or 3 and 8 and so on. You can easily decompose this into several stages and you find connectivity from the nodes of one stage to the next stage. So it is a simple shortest path problem, but we are going to use this problem to illustrate the concepts behind dynamic programming and the terminology that we are going to follow. Now the distances are also given here. So we have 5, 5 and 6, 2 to 5 is 4, 7 and 8, 8, 10 and 5, 4, 5 and 7, 6, 8, 9, 7, 5, 7, 8 and 9. Now we follow something called the backward recursive approach, that is, in order to reach 10, now this person has to either start from 8 or 9 and then the person has to go to 10. So we are right now assuming that the person is here and we call this one more stage to go, and the person is either at 8 or 9. Now the node or the place where the person is called the state of the system. So the state of the system is either at 8 or 9, and then given the state of the system, we try to find out the best decision that the person has to make at that stage to go from one stage to the next stage. And since we are following a backward recursion, we are going to say when we are here we have one more stage to go, when we are here we have two more stages to go, and so on. So the first table would look like this. We will have n equal to 1, one more stage to go, now S is called the state variable, and when we are here with one more stage to go, the state variable is either at 8 or at 9. The person can be either at node 8 or at node 9. And then the person has to make a decision which we call x1. X1 as the decision that is made when you have one more stage to go. Now whether the person is at 8 or the person is at 9, the decision is very clear to go to 10. Because there is no other destination. So in this case the x1, the decision is to go to 10, here also the decision is to go to 10, and then the value of the objective or the distance, this is a distance minimization problem. So the distance that the person will cover is given by f1, f1 is the distance function. Now f1 from S, in this case from 8 to 10 the distance is 8, and from 9 to 10 the distance is 9, and we have x1 star which is called the best decision, which will be to go to 10 whether you are going from 8 or from 9. Now right now, since we have only one alternative for x1, it automatically becomes x1 star, which is the best decision. So if the person is at 8, there is only one choice, which is to go to 10. So that is the best choice. So the person would travel a distance of 8 and go to 10, which is the best choice. If the person is at 9, then there is still only one choice, to go to 10, and the person will spend 9 or will travel 9 units and go to x1 star, which is 10. Now when we have n equal to 2, 2 more stages to go, which means we are, say, somewhere here. Now this is one stage, this is another stage. So there are 2 more stages to go. Now you will realize that there are more alternatives than one, 2 more stages to go. Now when there are 2 more stages to go, the various possibilities, when the person is here with 2 more stages to go, the person could either be in 5 or 6 or 7. So the state variable S takes 3 values, which is 5 or 6 or 7. Now when the person is in 5, person has to make a decision here. So the decision is where to go next, which is either 8 or 9. So now the x2, which is the decision that we have to make, can take 2 values, which is 8 and 9. Now when the person is at 5 and decides to go to 8, you incur a distance of 6 plus already the best way from 8 to reach the destination 10 is already written in the previous table. So you add another 8 to this. To repeat again, the state could be 5, 6 or 7. If the person is at 5 and decides to go to 8, now to travel from 5 to 8 you travel a distance of 6, and the best way to reach from this to the destination is already seen in the previous table. So if the person is at 8, then the best decision is to go to 10 to incur another 8. So 6 plus 8 equal to 14. Now if the person is at 5 and decides to go to 9, there is a distance of 8, and the best way to go from 9 to destination is already there in the previous table. So 9 to destination, additional distance of 9, so this becomes 8 plus 9 equal to 17. Now you have this is the state variable is at 5, the person is at 5, and in order to go from 5 to the destination, the person either goes through 8 or 9, and the total distance travelled from 5 to destination is already seen here. So the best thing the person would do is to travel a distance of 14 and go via 8, because this is the minimum distance. Now if the person is at 6 and decides to go to 8, there is a 9 here, and 8 to destination is already seen, which is the same 8 which is here. So this becomes 9 plus 8 equal to 17. If the person is at 6 and decides to go to 9, it is 7, and 9 to destination is already an additional 9, which is the same 9 here. So 7 plus 9 equal to 16, and the minimum of them is 16. So the total value is 16, and the best decision now is to go via 9 and not via 8. Similarly, if the person is at 7, then you have 5 to go to 8, and from 8 to destination is another 8, which is 13, and 7 plus another 9, which is 16, the smaller one is 13, and the decision is to go to 8. So we have now completed 2 of these stages. We have 2 more stages to go, like next the person would be here to make a decision, and then the person would come back to make a decision. But then since we have written a lot of numbers, let us try to define what we have actually written. So what we have here is this. So when I have one more stage to go, I define something called F1. I am in a state S or S1, you could define it suitably, we call it as S, and the person decides to go to X1. Now the value of the function that we are going to have is d s x1. So in this table the person is at 8, decides to go to 10, so the value of the function is d s x1, which is distance from 8 to 10, which is 8. Similarly from 9 to 10, which is 9. So the best decision here would be f1 star, which is the best decision for a given state S, is going to be the best one. So this will be the one that minimizes or minimize f1 s x1. Now in this case it will become much more obvious and clear. Now we have two stages to go. So f2, I am in a state S, I decide to go to city x2. Now that is d s x2. For example, if I am in 5 and decide to go to 8, it is d 5 8 plus the best way to reach from 8, which is f1 star of 8. f1 star of 8 is another 8 which is added here. So this will become plus f1 star of x2. From S I go to x2. So the from S to x2, from 5 to 8 I incur a distance of 6, and then once I reach 8, the best way to reach the destination from 8 is given by f1 star of 8. f1 star of 8 is this 8. So we add 6 plus 8, 14. Now when I am in state S equal to 5, I have two choices for x2 equal to 8 and 9. So I have evaluated this function as 14 and 17. So the best way to go from 5 to destination would be f2 star of S will be minimize f2 of S x2, and the corresponding x value is written as x2 star. So when I am in 5, now the best decision f2 star of 5, the best way to go from 5 to destination is f2 star of 5 is given by 14, and the corresponding x2 star is 8. So x2 star is the corresponding value of x2. So if I am at 5, the minimum distance to travel is 14 with the corresponding value of 8 from 5 to 8, 6, 16, the next destination is 9, and if I am at 7, the best way to reach is to travel 13 and go to 8. Now let us continue with the next three more stages to go. Which means I am here, so I could be either in 2 or 3 or 4. Now my state variable S can be in 2 or 3 or 4. My decision variable x3 can be to go to 5 or 6 or 7. So if I am in 2 and I decide to go to 5, from 2 to 5 the distance is 4 plus 5 to destination I have already found, which I can get from the previous table. So 5 to destination f2 star of 5 is 14. If I am in 2 and decide to go to 6, I have to travel 7 plus 6 to destination is already here minimum value of 16, and if I am in 2 and decide to go to 7, it is 8 plus from 7 to destination it is another 13. So this is 4 plus 14 is 18, 23 and 21. So the best value is 18 and x3 star is 5. If I am in 3 and I decide to go to 5, it is 8. 5 to destination is this 14, which is written here, so you can directly copy this 14. 3 to 6 is 10. 6 to destination is 16, which is already written here as 16, so 10 plus 16, and 2 to 7 is another 8. 8. 3 to 7 is, I am sorry, so 3 to 7 is 5, so I have a 5 here, and 7 to destination is 13. So this is 22, 26 and 18, and the minimum is 18 and the best decision is to go to 7. Now if I am at 4, then I incur 4 to 5 is 4, 5 to destination is already here as 14, the same 14 here, 4 to 6 is 5, 6 to destination is 16, which is here as well as here, and 4 to 7 is 7, 7 to destination is 13, same 13 that is here as well as here. So the values are 18, 16 plus 5 21 and 20, so it is again 18 and the best decision is to go to 5. Now we also have to write down the equations. So F3, 3 more stages to go, I am at state S and I decide to go to x3. Now this will be dsx3 plus, we go back to the previous stage and find out the best value. So F2 star of x3 and F3 star for a given S will be to minimize F3 of x3 and x3 star equal to corresponding x3. Now we go to the last part, n equal to 4, 4 more stages to go. Which means we are here, the person is at the beginning, which is in city 1, so state variable has only one value. So right now we are here, S is 1. Now from 1 the person can go to either 2 or 3 or 4, so you would have x4 can take values 2 or 3 or 4. So 1 to 2 is 5, 2 to destination is already here, which is given as F3 star of 2, which is another 18, 1 to 3 is another 5, and 3 F3 star of 3 is again 18, so 3 to destination is another 18. Now 1 to 4 is 6 and 4 to destination is also 18. So F4 star of S is 23 and x4 star is 2 and 3. Now we have to write down the equations. So we write F4 of Sx4 is equal to d Sx4 plus F3 star of x4, indicating that if I am in S and decide to go to x4, I travel a distance from S to x4 plus the shortest distance from the x4 to destination is given in the previous table, so F3 star of x4. Now F4 star of S is to minimize F4 of Sx4 and x4 star equal to corresponding value. Now we have solved the problem. Now the shortest distance is 23 from 1 to 10, and there are 2 paths. So we start from 1, you could go to 2 from this, or from 1 you could go to 3, Now go back to this table and see, if I am in 2, the next destination is 5, if I am in 3, the next destination is 7. So 1 to 2, 2 to 5, 1 to 3, 3 to 7. This table will tell you, if you are in 5, the next destination is 8, if you are in 7, the next destination is 8, and this table will tell you, if you are in 8, the next destination is 10. So there are 2 paths here which are the shortest paths, which have a total distance of 23. We also need to introduce some terminology which is consistent with all DP problems, which we will do now. We have to define 4 terms which are called stage, state, decision variable, and criterion of effectiveness. Now these 4 parameters are common for every DP problem and have to be defined for each problem. Now this problem, stage is actually a stage, in the sense that we have defined the problem in such a way that the person goes from one stage to another. Each stage is characterized by a set of alternatives or cities that are available. So here each is a stage. So stage is actually the stage of decision making. State here is, at every table you realize the state is the place where the person is already, from where he or she has to make a decision. So state is city at which the city which the person presently is, or you can say city in which the person is located. Decision variable is the next destination, where to go next, and the criterion of effectiveness, it is a minimization problem. So we need to minimize total distance traveled. So now we have completed this problem or solved this problem using DP. Now dynamic programming involves certain things. Now first thing is we solve the problem stage wise. So even before we do all this, the first thing we need to do is to write down the stage, state, decision variable and criterion of effectiveness. Maybe for this example and perhaps the next example we will try to write this in the end, but then as we proceed with more examples, it is absolutely necessary that we define this first. In fact, once the state variables and decision variables are defined, the problem becomes easy to solve. Here, since we are introducing the terminology, we solve the problem and then later said that these 4 terms have to be introduced for every problem. In fact, the first thing we need to do is to introduce these 4 terms and define them to the specific problem. Then we follow what is called a backward recursive approach. In the sense we assume that we have reached the destination and then we go backwards and see that in order to reach 10 you need to go one stage back, and you can start from 8 to 9, which is the first one, second, third and fourth respectively. Each stage the calculations are shown in the form of a table here, because the state variable and the decision variables take discrete values, they are not continuous variables. So here the state could be either 8 or 9 and decision is to go to 10. Here state is discrete values 5, 6 and 7 and decision is two values 8 or 9, no other continuous variable. So we follow a tabular approach, and for every table we have to define what is in the table, we have to define the relationship. Now this relationship is called recursive relationship. Now you could define a recursive relationship for every table as we have done, or you could write a general recursive relationship for this problem, which would be like this, consistent with our terminology. It will be like this: Fn, f is the function, n more stages to go, I am at state s and decide to go to xn. Xn is a decision variable, s is a state variable. Then I travel a distance of d s xn from s to xn, and then I go to the previous table f n minus 1 star, which is the best value of xn. For example, if I am in 5 and decide to go to 9, then somewhere we would have this here. I am in 5, I decide to go to 9. So you see, I have 2 more stages to go. So Sx2 is dsx2 plus f1 star of x2. So the best value is taken from the previous table. So if I have n more stages to go, I go to the previous table, which is n minus 1 star of xn, and the best value would be fn star, n more stages to go. Given state S, the best value is the one that minimizes fn of Sxn, and the value of xn star is the corresponding xn for which this value is minimum. So this kind of completes the first example along with the terminology that we will use. We will now take few more examples, at least a couple of more examples for the discrete case, and then we would also look at some more examples where the decision variables take continuous values. So let us look at the second example here. Second example is what we call as the reliability problem. Here we assume that we have an equipment which is made up of say 4 components. We call them A, B, C and D, which are connected in series in order for the equipment to function. Now each component has a certain reliability in a series system. So total reliability of the system is the product of the individual reliabilities. Now in order to improve the reliability, we can also add another component in parallel or keep them as a standby and so on. For example, we could add another A here or use it in such a way that the reliability of A together is increased and therefore the overall reliability is increased. Now we have the data that tells us for this problem. The data is like this. Now for these 4 components, the number of units that we could have could be 1, 2, 3 and 4. Now this is component A. So we have 2 terms, reliability and cost, C and D, reliability and cost, 0.6, 100, 0.7, 130, 0.8, 150, 0.9, 170, 0.7, 80, 0.75, 100, 0.8, 120, 0.85, 140, 0.7, for example, if we have these 4 components here, If I have only one of A, I get a reliability of 0.6, I have to spend 100 rupees. If I decide to add another one of A here, then I would have to spend 130 and the total reliability of this A alone will be 0.7 and so on. Similarly, if I decide to put say 2 of C, then I get a reliability of 0.8 and the cost is going to be 80. So obviously there is a restriction on the amount that we have that we can spend, and that is given by rupees 300. Excellent. Yeah, we assume that rupees 400 is available as amount, and we try to solve this problem. So the problem now is how many units we will have of A, B, C and D such that we maximize the total reliability of this system. At the same time, we have a budget restriction or the money restriction of rupees 400 with us. So as we start, we realize that we first have to define the 4 important terms: stage, state, decision variable, and criterion of effectiveness. Now as far as this problem is concerned, if we follow a backward recursive approach, then when we have one more stage to go, we would be somewhere here. If we have 2 more stages to go, then we will be here, 3 more will be here, 4 more will be here. So as far as this problem is concerned, stage is each component, because we make a decision for every component as we follow a backward recursive. So stage is component, now decision variable is easier to define in this than the state variable. So we define this and then we come back to this. Now decision variable is how many units are we going to have for each one of these components. So decision variable would be how many units. Criterion of effectiveness is the objective function with which we begin. The objective is to maximize the reliability. So criterion of effectiveness is to maximize reliability. Now what is a state variable? State variable in this example is the amount of money available for allocation, because the decision is going to be based on the resource that we have, and the resource in this case is the money. If we have unlimited money, then the decisions are obvious, try to put the maximum. But because there is a money restriction, depending on how much money that is available to make a decision in every stage, the decision variable changes. So state in this example is the amount of money available, or in general wherever there is a constraint, the resource availability represents the state of the system. State can directly be linked to resource availability. In this case, state variable is the amount of money that is available for allocation to that particular component. So having defined these 4, let us go back and try to solve this problem. Now when we have n is equal to 1, one more stage to go. We call it as x1, or we call x4 as the number of units that we are going to have of D, x3 for C, x2 for B and x1 for A. So x4 is the variable which says how many units of D. Then we have f4 of x4 or f1 star of x4, and then we have the corresponding x4 star. Now what are the possible values that the state variable can take if I have one more thing to go? Now one easy thing to say is we can say the money that is available for allocation of D could be anything from 0 to 400, but we do not follow that. We try to see what is the bare minimum that we need and what is the maximum that we can have. Now as far as this is concerned, the bare minimum money that we need is enough money to buy at least one of D, which is at least 60. So we need to start with at least 60, otherwise we will not be able to buy even one of D and the equipment will not function. So it does not make sense to look at state variables of 0 to 59 for this, because we cannot buy anything of D and the reliability will be 0. So it makes sense to start with saying that I will have at least one of each A, B, C, D there, which I will have to buy, and over and above that whatever money I have I try to spend on buying more of A, B, C, D. So the minimum money that I need to have here is 60. The maximum money that I can have for D is actually if I had bought only one of A, B and C, which means if I had spent exactly 100 on A, 80 on B, 75 on C, which is 255, if I had spent, then the balance 145 is the maximum that I could have for D. So D, the maximum that state variable will have here is 145, because if I have anything more than 145 allocated for D or available for allocation to D, it means that I will not be able to buy one of A, one of B, one of C, and therefore my reliability will be 0. So I make an assumption that I have at least one of A, B, C and D, therefore the resource that is available for D can vary anything from 60 to 145. Now if it is from 60 to say 70 or 69, then I can buy only one of this, so x4 is 1 and the reliability is 0.8 and x4 star is 1. When I have between 60 and 69 rupees, I can buy only one of D, therefore my reliability is 0.8 for D and I buy exactly 1. So when I have 70 to 74, I can buy 2 of D, that is what I will do. I will not buy one of D and keep the remaining money unutilized. The reason is by buying 2 of D I can increase the reliability of D and the overall reliability of the system. So I will not consider here, if I have more than 70, I will not consider the possibility of buying only one of D and keeping the remaining money unspent. So we try to buy as much of D as possible, because the objective is to maximize reliability, not to minimize the money spent. So the decisions are made always keeping in mind the criterion of effectiveness, which is the objective function. So when state is from 70 to 74, x4 will be 2 and I can have a reliability of 0.85 and x4 star will be 2. Even though there are two alternatives here, which is x4 equal to 1 and 2, the best value will be 2. Now similarly, when I have 75 to 79, that is enough money to buy 3 of D, so x4 is 3, reliability is 0.88 and x4 star is 3. And when I have anything greater than 80, so 80 to 145, I will have 4 of this to get 0.90 and I have 4 of this. Now what is the recursive equation here? Recursive equation is f1 of s comma x1. I have s rupees available, x4, I have s1 rupees available, or yes, you could use it suitably. If you use s1 here, we will have s1 here, that is it. And this will be f1 star of s or s1. So we use s here, so you could consistently use s. So I have one more stage to go, one decision to make, that is D. If I am left with s rupees and I decide to buy x4 units of D, then this will be reliability associated with x4. For example, if I have 70 to 74, I can buy a maximum of 2, so I go back and see that my reliability is 0.85. Now what is the best value given? So f1 star of s will be maximize R of x4 subject to the condition C of x4 should be less than or equal to Yes. For example, when I have state variable, say suppose I have 72 rupees available here, now I can buy 2, yes, as long as the money that I have for 2, which is 70, is less than the state variable. So this constraint has to be satisfied by the best value, and the best value x4 star will be the corresponding value of x4. Now when we go back and try to solve for this C and D put together, which means we have 2 more stages to go. So we are at n equal to 2, 2 more stages to go. Now we have the state variable S, and you could have decision variables. This is x3 equal to 1, 2, 3 and 4. There are 4 alternatives that are possible. Then we have f2 star of S, and we have x3 star. Now what is the minimum value that S can take when I am here? When I have 2 more stages to go, the minimum amount of money that I definitely need should be sufficient to buy at least 1 of C and 1 of D. So this would begin with 75 plus 60, which is 135, and the maximum would be if I had bought 1 of A and 1 of B. So if I had bought 1 of A and 1 of B and spent 180, then we had 400, so the maximum I could have would be 220. Now let us complete this table. Now when I have exactly 135 here and I buy x3 equal to 1, so x3 equal to 1 gives me a reliability of 0.7, and I spend 75 on this. So the balance money that I have out of the 135 is 60, 135 minus 75, which is 60, which I carry to the next item. So when I have 60, I get another reliability of 0.8, which I have. Now when I have 135, I decide to buy 2 of C, which means I spend 80. I have the balance 55 available for this. I cannot buy anything, so I do not look at this alternatives, all the 3 alternatives. So when I have 135, I have only one alternative, which gives me a reliability of 0.56, and x3 star is 1. Now when I have 136, now what we need to do is, we need to look at all the state variable values from 135 to 220, which is roughly about 66 plus 20, 86 different values that we need to look at. So we do not tabulate all 86 here, we try to bring them into the range like what we did here. So now we look at 136, when we are at 136 the same thing will happen. For example, I can buy only 1 of C and spend 75, I would have a balance of 61, from which I go to this range and I could have only 1 of this. So this will happen from 135 to 139. I will have only one possibility that exists, I will be able to buy only 1 of C and get this. Now when my state variable moves to 140, now what will happen is, I could have 2 alternatives. I could buy 1 of C, spend the 75, get 0.7, the balance would be spend 75 out of 140, so the balance would be 65, so 65 would give me again 0.8, but I can do another thing, I can spend 80 and buy 2 of C to get 0.8. I have already spent 80, so I carry the remaining 60 to the next one, so at 60 I get another 0.8, so this becomes 0.64, Now these two are not possible. Now the best decision here between these two is 0.64 and x3 equal to 2. Now like this we have to build this table. Now wherever we find another alternative coming in, we move to the next definition of the state. Now we show the entire table here. Now when I have from 140 to 144, my best decision is 0.64. Now from 145 to 149, that is the next range, and there I realize that I could get into a third alternative, which is here. Now this alternative is trying to buy 3 of C and spending 85, and with the remaining 60 buying 1. So from 145 to 149 we have 3 alternatives, and the best value is 0.72 with x3 star equal to 3. Now similarly I move again from 150 to 154. I have one more alternative that comes in. Now when I am at 150, I could think of x3 equal to 4, which means I could think of buying 4 of C, spending 90, getting a reliability of 0.95, and with the remaining 60 I buy 1 of this. Now that is given as the fourth option here, which gives me 0.95 from here, and the remaining 60 would give me 0.8. So 0.95 into 0.8 gives me a 0.76. So this gives me 0.76, and the best alternative is still with 0.76 and 4. Now when I am in the range 155 to 159, now all the 4 possibilities exist for buying C, but then one of the values would change. One could see that when you are 155, 159, if you decide to buy 1 here and spend 75, you get a balance 80, so you are moving into this range to get a reliability of 0.9. So you get 0.7 into 0.9, which is 0.63. This would be 0.8 into 0.88. If I buy 2 and spend 80, and then I have a 75, so I move into this range, so I get 0.8 into 0.88, which is 0.704. So all the 4 alternatives exist, but they have different reliabilities. So the best value would be 0.765, and this happens when x3 star equal to 3, which is shown here. Now again at 160 to 164 we need to calculate. So at 160 to 164 we realize that the change actually happens here, 0.9 into 0.88 and 0.95 into 0.85. So if I am at 160 and I decide to buy 3, I have 85 plus 75, so I move into the next range. If I decide to buy 4, I have 90, giving me 0.95 into 0.88, which gives me 0.8075. So when I am at 160 to 164, I have 0.8075, which comes as the maximum reliability, and my decision would be to buy all 4. Similarly, when I am at 165 to 169, I again have all 4 possibilities, and the best value would be 0.836 with x3 star equal to 4, and I am from 170 to 220, I realize that it is 0.855, x3 star equal to 4. Now we have not shown the individual calculations in this table, but we have shown the individual calculations in the other table, and one needs to go back and see that if I am in a particular range and all the 4 decisions are possible in this case. Now depending on the decision, you have to see what is the money that is spent here, and then carry the balance money to the previous table and find out the best decision. We will just write down the recursive relations for these two for the second one right now. So if I have 2 more stages to go, if I have S rupees, which is my state variable, and decide to buy x3 units of this. So, I will have R of x3 plus or multiplied by f1 star of s minus c of x3. For example, just to calculate say something like this. If I have 160 with me and say I decide to buy 4 here, then I have 160, for 4 I spend 90 and get a 0.95 here. I spend 90, I have a balance of 70, this 70 would give me another 0.85, which is from 0.8075. So, like this we actually complete this table. The most important thing here is that we have s minus c of x. I start with s, I spend some c which is cost, the balance I carry to the previous stage and I put f1 star of s minus c x3. So, we have right now completed 2 stages, there are still 2 more stages in this problem. We look at the other 2 stages in the next lecture.